Hello, I'm Luc Estebanez. I'm a researcher in neuroscience and neural engineering at Université Paris-Saclay, France. Together with Valérie Ego-Stengel, a colleague of mine, we recently published a paper showing that you can't just provide any feedback to a subject through a brain-machine interface. You have to follow rules. So let me give you some context first. Brain-machine interfaces are devices that are able to connect directly the brain of a subject to an artifact, to a robot, for instance, to a prosthesis. And using this tool, it is possible for a patient that is tetraplegic, that is highly dependent on others, to regain autonomy. And this is a future that's getting increasingly promising as bidirectional brain-machine interfaces are being developed that combine the readout of neuronal activity as a command to control a prosthesis and combine this with feedback from the prosthesis to the user. So why is feedback so important? Well, if you use a prosthesis to interact with your environment, you want to be able to move the prosthesis, but just like a physiological leg, you want also to be able to perceive if the prosthesis touches its environment, not only because you want to be safe and you don't want to break everything around you, but also because touch is a very important sensation to explore your environment, to know better about your environment, and to, for instance, perform very skilled, fine motor tasks with your hand. You cannot play the piano without having tactile feedback from your hand. And so there is an increasing interest in developing tactile feedback from a prosthesis, from touch sensors, artificial touch sensors in the prosthesis, and to the brain. And there are simple, straightforward ways to do that, and that can be to connect directly each of the touch sensors to the brain in the form of a microstimulation of the brain. However, when researchers have done that, they have found that it was very difficult for the brain of the patient to discriminate between the different touch inputs that were provided. And it was not so clear why this was the case. And so what we have done in the study we just published is that we have moved to the mouse model, and there we have tried to interrogate what are the constraints that the mice face when they want to integrate and take into account in a sensory motor task the information that's provided to them through direct stimulations of the brain. And what we have found when doing that is that the spatial and temporal organization of the stimulation of the brain that we provided to the mice had a tremendous impact on the mice's ability to take into account this information to solve a task. So basically we use optogenetics, which is a method that allows to activate neurons with light to basically shed on the cortical surface, on the brain surface, distributed patterns of light that carried information about a task that the mouse had to perform using a brain-machine interface. And we found that if the pattern of light was continuous in time and in space, then the mice were really able to take the information that was carried in these patterns very efficiently to solve a task and obtain a reward. But now, if the structure of the feedback was disrupted, was scrambled, while still maintaining the same information, but this time without the continuity in space or in time, then the brain of the mice turned out to be unable to integrate this information, and therefore the mice were unable to perform the task that we trained them to do. This has led us to conclude that when designing the next generation of bidirectional brain-machine interfaces, it will be critical to design feedbacks very carefully by taking into account this newly found constraint. So obviously there is a perspective there towards a user to connect the mice to an actual prosthesis and probe whether when using these actual prostheses to solve tasks, the same constraints apply. So that's our next step. Thanks for listening, and hope you have a great day. Bye.